Hello everyone. Today we're going to be looking at Lab 3, which is the design of the common emitter amplifier. For this lab, we're basically choosing the different resistor values in this circuit in order to meet the differential gain requirement, supply voltage, and output swing requirement. And they tell you what beta is for the transistor and what the collector current is, which is 6 milliamps. You can also assume VBE is 0.7 volts for this. So the lab gives you step-by-step instructions on how to do this, and we're just going to go through those together. So the first step is they just give you all these inputs that I just mentioned. The next step, it says to pick a supply voltage, VCC, and desired voltage gain. So you can just kind of go in the middle maybe, or you can pick your own values between 20 and 30 for the gain and 14 and 16 for the supply voltage. So the next step is the actual design. First, it says to choose a value of RC to meet the output swing spec. So the output swing has to be peak to peak your supply voltage minus 5. So if you chose 10 volts for the supply, then, or if you chose 15 volts for the supply, then the output swing has to be 10 volts peak to peak. So let's think about this. The output swing, that means you have to swing high and low a certain amount. If 10 volts peak to peak, then you have to be able to swing high 5 volts and low minus 5 volts around the DC operating point. But the resistor is basically there just to choose the DC operating point of that node, which we'll call VC, the collector voltage. So the DC operating point is, if we just do Ohm's law, VCC minus VC equals IC times RC. It's just Ohm's law. And we need to choose RC to satisfy this equation, but we need to choose what VC will be. So, for example, if VCC equals 15 volts, and that means our output swing equals 10 volts peak to peak. If we look at this on a graph, we need to choose a DC voltage, which we'll call VC, and we need to be able to swing around that 10 volts peak to peak. And that means the amplitude will be 5. So what is the maximum value of VC that we could choose in order to make that happen? Well, if we choose 10 volts here, then the peak would be 15 volts, which is just at our supply voltage in the case that I'm talking about. So that is the highest value of VC that would get this amplifier to swing 10 volts peak to peak. So really you'd probably want to put this a little below that. So you might choose VC equal to 9 volts, such that it can swing high 6 volts before it hits the positive rail. So let's try that in this case. And so 15 volts minus 9 volts is what I chose, 6 milliamps times RC. And you can calculate RC from that. And that'll be pretty much the same for everyone's design, regardless of what VCC you choose. You're going to end up with basically the same answer here. Everyone will have the same result. So that's how you get RC. Next, it says to choose the base voltage within some parameters that they tell you. So we're just going to choose the base voltage. We're just going to choose to be in the middle, 0.25 times VCC, just to keep things simple. So now you'll know the base voltage. And this is the emitter voltage up here. I just labeled the nodes. So this was step 3, this was step 4. Step 5, set I1 equal to 10 times IB. I1 equals 10 times IB. And then figure out what R1 is. Okay, so this is just going to do Ohm's law again. So IB is equal to roughly IC over beta. And you know IC is 6 milliamps. Beta is 150. So you can figure out what IB is. Once you know IB, then you can figure out what I1 is. Once you know I1, you can figure out what R1 is, just using Ohm's law. It'll be VCC minus VB, which you chose in the last step, equal to I1, which we just solved for, times R1. And that will give you R1. Part 6 is pretty similar for R2. So I2 is equal to 9 IB. And figure out R2. So you can do the same steps here. We've already calculated IB in the previous part. So I2 is equal to 9 times IB. And that'll give you a value. Then Ohm's law again, across R2. This time we have VB minus 0 equal to I2 R2. And you can solve for R2 from that. Alright, so now we just got the emitter resistors to figure out. Let's see. Okay, so this one's saying solve for the sum of RE1 and RE2. So the base voltage we chose in part 4, and we can quickly figure out the emitter voltage based on that. So remember that VBE is equal to VB minus VE. And so VBE is given as 0.7. Base voltage we figured out in part 4. We can solve for the emitter voltage. So just 0.7 volts below the base voltage. So if you know the emitter voltage, then it's just Ohm's law across those two resistors. So VE minus 0 equal to, if you assume the emitter current and collector current are the same, you can just use that here. And that's times RE1 plus RE2. So RE1 plus E2 equals VE over IC. And you can calculate that. The next part is we need to determine at least one of those so we can figure out what the other one is. And the only thing we haven't really used yet is the gain equation. And you chose a gain at the start of this, so we're going to use that now. The gain for this circuit is approximately equal to RC parallel RL divided by RE, little re, plus RE1, where little re is equal to VT, the thermal voltage, divided by IC. So you can calculate that pretty quickly since you know the current. RC you calculated in part 3. RL is given 10 kilo ohms. RE you just calculated, and you chose AV, so you can calculate what RE1 is based on that. And so solve this for RE1. Once you know RE1, you can go back to this up here, which gave you the sum of RE1 plus RE2, and that will give you RE2. And that's it. You will have all the resistor values. The last step in the process is to round all of these to standard values based on what you can actually find in the lab, which is pretty straightforward. Just make sure you round in the correct direction sometimes. For example, RC, if you round that up, that would be the way to go. But if you happen to round it down, then you will have less IR drop across RC if this resistance was less, which would make this VC node go higher, and then you might not be able to meet your swing spec if that voltage gets too close to the rail. So RC you'd want to round up so that VC ends up going further below VCC, more IR drop. R1 and R2 are pretty insensitive, they're not too important. RE1, if you make him, let's see, you have a specific gain requirement, and I think you have to be within plus or minus 10% of that. So it doesn't really matter which way you round, but if you round RE1 down, then your gain will go up. If you round him up, then your gain will go down because he's in the denominator. So you can be a little choosy with that too. And that's it. The next part is to verify this with a simulation to make sure it works correctly.